Okay, now we have this bunch of theorems in a big box here, and we want to structure the space somehow. Now, we kind of started fresh, and we took a new approach, and we just kind of designed a space where these theorems are points. So if you look at mathematics, then, well, Cantor started set theory, I don't know, around the 1880s. And so from then on, sets were studied, sets of numbers and so on. In the 1920s, people went on to sets of functions, function spaces, and functional analysis became very important. And so I think it's a consequent and kind of convincing step to look also at spaces of theorems, where the individual points in the space are theorems. And I will tell you how we actually can achieve such a thing. And then our approach is just to study the space of theorems with classical mathematical methods. So in a certain sense, we don't use any logic whatsoever, at least not in any other way as a classical mathematician does that. I mean, somebody who does analysis or topology, of course, uses logic, but not in a formal sense, just in an informal sense. And that's exactly the way we use logic too. So this is in a certain sense not logic. It's really computational meta-mathematics in a purely mathematical way. Okay, now in order to explain to you how we actually design the space, I will take some further steps back. I will look at logical implication. So I look at logic again. In a certain sense, one would expect that logical implication is a tool to compare theorems. So you all know the truth table of logical implication. This is how we teach logic to beginners, to students. Now, surprisingly, this is not the way mathematicians use logic. So if you do a phenomenological study of how mathematicians use logic, then you will see that this is not the way that they are using logic. So we looked at this book. It's a typical textbook on applied mathematics, in this case on partial differential equations, and then you find this funny little lemma here in this book. Lemma 8.36 says the open mapping theorem, the bounded inverse theorem, and the closed graph theorem are equivalent. Now, if you use the definition of implication that I have just shown to you, then this is nonsense, because of course every correct theorem is equivalent to any other correct theorem. So the theorem of Pythagoras is equivalent to Fermat's last theorem, and so on. Obviously, the authors of this textbook, they are not stupid, so they have had something in mind when they said that these theorems are equivalent. And if you look at the proof, I can't read it, but it's a copy of it. If you look at the proof of what they actually did there, then they showed that these theorems are very closely related to each other in the sense that you can directly derive one theorem from the other in a very direct sense. However, they never formalized what this means to do that in a direct way, so they never gave a precise definition of what they meant by equivalence. Okay, so it seems that in applications, mathematicians occasionally use the notion of implication and equivalence in a slightly different way from our logical definition, namely in the sense that there is a direct method to derive B from A, as the interpretation of A implies B.